Thrust vectoring, also thrust vector control or TVC, is the ability of an aircraft, rocket, or other vehicle to manipulate the direction of the thrust from its engine, or motor in order to control the attitude or angular velocity of the vehicle. In rocketry and ballistic missiles that fly outside the atmosphere, aerodynamic control surfaces are ineffective, so thrust vectoring is the primary means of attitude control. For aircraft, the method was originally envisaged to provide upward vertical thrust as a means to give aircraft vertical or short takeoff and landing ability. Subsequently, it was realized that using vectored thrust in combat situations enabled aircraft to perform various maneuvers not available to conventional engine planes. To perform turns, aircraft that use no thrust vectoring must rely on aerodynamic control surfaces only, such as ailerons or elevator. Craft with vectoring must still use control surfaces, but to a lesser extent. In missile literature originating from Russian sources, thrust vectoring is often referred as gas dynamic steering, or gas dynamic control. Thrust vectoring methods, rockets and ballistic missiles. Thrust vector control is effective only while the propulsion system is creating thrust. At other stages of flight, separate mechanisms are required for attitude and flight path control. Nominally, the line of action of the thrust vector of a rocket nozzle passes through the vehicle's center of mass, generating zero net moment about the mass center. It is possible to generate pitch and yaw moments by deflecting the main rocket thrust vector so that it does not pass through the mass center. Because the line of action is generally oriented nearly parallel to the roll axis, roll control usually requires the use of two or more separately hinged nozzles or a separate system altogether, such as fins, or vanes in the exhaust plume of the rocket engine, deflecting the main thrust. Thrust vectoring for many liquid rockets is achieved by gimbling the rocket engine. This often involves moving the entire combustion chamber and outer engine bell as on the Titan II's twin first-stage motors, or even the entire engine assembly including the related fuel and oxidizer pumps. Such a system was used on the Saturn V and the Space Shuttle. Another method of thrust vectoring used on early solid propellant ballistic missiles was liquid injection, in which the rocket nozzle is fixed, but a fluid is introduced into the exhaust flow from injectors mounted around the aft end of the missile. If the liquid is injected on only one side of the missile, it modifies that side of the exhaust plume, resulting in different thrust on that side and an asymmetric net force on the missile. This was the control system used on the Minuteman II and the early SLBMs of the United States Navy. A later method developed for solid propellant ballistic missiles achieves thrust vectoring by deflecting the rocket nozzle using electric servo mechanisms or hydraulic cylinders. The nozzle is attached to the missile via a ball joint with a hole in the center, or a flexible seal made of a thermally resistant material, the latter generally requiring more torque and a higher power actuation system. The Trident C4 and E5 systems are controlled via hydraulically actuated nozzle. Tactical missiles and small projectiles, some smaller-sized atmospheric tactical missiles, such as the AIM-9X Sidewinder, eschew flight control surfaces and instead use mechanical vanes to deflect motor exhaust to one side. Thrust vectoring is a way to reduce a missile's minimum range, before which it cannot reach a speed high enough for its small aerodynamic surfaces to produce effective maneuver. For example, anti-tank missiles such as the EOYX and the PARS-3LR use thrust vectoring for this reason. Some other projectiles that use thrust vectoring, 9M330, Strix mortar round uses 12 midsection lateral thruster rockets to provide terminal course corrections. Aster missile family combines aerodynamic control and the direct thrust vector control called PIF-PAF. AIM-9X uses 4 jet vanes inside the exhaust that move as the fins move. 9M96E uses a gas dynamic control system enables maneuver at altitudes of up to 35 km at forces of over 20 g, which permits engagement of non-strategic ballistic missiles. 9K720 Iskander is controlled during the whole flight with gas dynamic and aerodynamic control surfaces. Aircraft, most currently operational vectored thrust aircraft use turbofans with rotating nozzles or vanes to deflect the exhaust stream. This method can successfully deflect thrust through as much as 90 degrees, relative to the aircraft center line. However, the engine must be sized for vertical lift, rather than normal flight, which results in a weight penalty. Afterburning is difficult to incorporate and is impractical for takeoff and landing thrust vectoring, because the very hot exhaust can damage runway surfaces. Without afterburning, it is hard to reach supersonic flight speeds. A PCB engine, the Bristol Siddeley BS-100, was cancelled in 1965. Tilt-rotor aircraft vector thrust via rotating turboprop engine nacelles. The mechanical complexities of this design are quite troublesome, including twisting flexible internal components and drive shaft power transfer between engines. Most current tilt-rotor designs feature two rotors in a side-by-side configuration. If such a craft is flown in a way where it enters a vortex ring state, one of the rotors will always enter slightly before the other, causing the aircraft to perform a drastic and unplanned roll. Thrust vectoring is also used as a control mechanism for airships. An early application was the British Army airship Delta, which first flew in 1912. It was later used on HMA No. 9R, a British rigid airship that first flew in 1916, and the twin 1930s-era U.S. Navy rigid airships USS Akron and USS Macon that were used as airborne aircraft carriers, and a similar form of thrust vectoring is also particularly valuable today for the control of modern non-rigid airships. In this use, most of the load is usually supported by buoyancy, and vectored thrust is used to control the motion of the aircraft. But, designs have recently been proposed, especially for Project Walrus, where a significant portion of the weight of the craft is supported by vectored thrust. The first airship that used a control system based on pressurized air was Enrico Forlanini's Omnia Deux in 1930s. A design for a jet incorporating thrust vectoring was submitted in 1949 to the British Air Ministry by Percy Wallin. Official interest was curtailed when it was realized that the designer was a patient in a mental hospital. Now being researched, fluidic thrust vectoring diverts thrust via secondary fluidic injections. Tests show that air forced into a jet engine exhaust stream can deflect thrust up to 15 degrees. Such nozzles are desirable for their lower mass and cost, inertia, complexity, and radar cross-section for stealth. This will likely be used in many unmanned aerial vehicle, and sixth-generation fighter aircraft. Nozzles. Thrust vectoring flight control is obtained through deflection of the aircraft jets into the pitch, yaw and roll directions. In the extreme, deflection of the jets in yaw, pitch and roll creates desired forces and moments, enabling complete directional control of the aircraft flight path without the implementation of the conventional aerodynamic flight controls. When TVFC is implemented to complement CAFC, agility and safety of the aircraft are maximized. To implement TVFC, a variety of nozzles, both mechanical and fluidic, may be applied. This includes, but is certainly not limited to, convergent and convergent-divergent nozzles that may be fixed or geometrically variable. Within these aircraft nozzles, the geometry itself may vary from two-dimensional to axisymmetric or elliptic. Thus, it is necessary to clarify some basic definitions used in thrust vectoring nozzle design. Axisymmetric, nozzles with circular exits. Conventional aerodynamic flight control, pitch, your pitch roll or any other combination of aircraft control through aerodynamic deflection using rudders, flaps, elevators and/or ailerons. Converging diverging nozzle, generally found on fighter aircraft, the jet stream is taken through a reduction in area to achieve Mach 1 and then expanded through a diverging section to achieve a supersonic speed greater than Mach 1 before issuing forth. Converging nozzle, nozzle used on standard subsonic transport and passenger jet aircraft. After the turbine, the nozzle converges to the designed exit area where the jet stream issues forth at Mach 1 or less. Effective vectoring angle, the average angle of deflection of the jet stream centerline at any given moment in time. Fixed nozzle, a thrust vectoring nozzle of invariant geometry or one of variant geometry maintaining a constant geometric area ratio during vectoring. This will also be referred to as civil aircraft nozzles and represents the nozzle thrust vectoring control applicable to passenger, transport, cargo and other subsonic aircraft. Geometric vectoring angle, geometric center line of the nozzle during vectoring. For those nozzles vectored at the geometric throat and beyond, this can differ considerably from the effective vectoring angle. Nozzle, either convergent or convergent divergent nozzles, focusing on those generally implemented in aircraft. Pitch, vertical directional movement of the nozzle exit or nose of the aircraft. Roll, circular directional movement of the aircraft around the body axis vector. Thrust vectoring, the deflection of the jet away from the body axis through the implementation of a flexible nozzle, flaps, paddles, auxiliary fluid mechanics or similar methods. Thrust vectoring flight control, pitch roll or any other combination of aircraft control through deflection of thrust generally issuing from an air-breathing turbofan engine. Two-dimensional, nozzles with square or rectangular exits. Two-dimensional converging diverging, square or rectangular supersonic nozzles on fighter aircraft. Variable nozzle, a thrust vectoring nozzle of variable geometry maintaining a constant effective nozzle area ratio, during vectoring. This will also be referred to as military aircraft nozzles and represents the nozzle thrust vectoring control applicable to fighter and other supersonic aircraft. Yaw, horizontal directional movement of the aircraft or nozzle. Methods of nozzle control, geometric area ratios maintaining a fixed geometric area ratio from the throat to the exit during vectoring. The effective throat is constricted as the vectoring angle increases. Effective area ratios maintaining a fixed effective area ratio from the throat to the exit during vectoring. The geometric throat is opened as the vectoring angle increases. Differential area ratios maximizing nozzle expansion efficiency generally through predicting the optimal effective area as a function of the mass flow rate. Methods of thrust vectoring, Type IA nozzles whose bearer frame mechanically is rotated before the geometrical throat. Type II nozzles whose bearer frame is mechanically rotated at the geometrical throat. Type III nozzles whose bearer frame is not rotated. Rather, the addition of mechanical deflection post-exit vanes or paddles enables jet deflection. Type IV jet deflection through counter-flowing or co-flowing auxiliary jet streams. Fluid-based jet deflection. Operational examples. A famous example of thrust vectoring is the Rolls-Royce Pegasus engine used in the Hawker Siddeley Harrier, as well as in the AV-8B Harrier II variant. Widespread use of thrust vectoring for enhanced maneuverability in Western production model fighter aircraft didn't occur until the deployment of the Lockheed Martin F-22 Raptor 5th-generation jet fighter in 2005, with its afterburning, thrust vectoring Pratt & Whitney F-119 turbofan. Lockheed Martin F-35 Lightning II is currently in the pre-production test and development stage. Although this aircraft uses a conventional afterburning turbofan to facilitate supersonic operation, the F-35B variant, developed for joint usage by the U.S. Marine Corps, Royal Air Force, Royal Navy, and Italian Navy, also incorporates a vertically mounted, low-pressure shaft-driven remote fan, which is driven through a clutch during landing from the engine. Both the exhaust from this fan and the main engine's fan are deflected by thrust vectoring nozzles, to provide the appropriate combination of lift and propulsive thrust. The Sukhoi Su-30 MKI, produced by India under license at Hindustan Aeronautics Limited, is in active service with the Indian Air Force, and employs 2D thrust vectoring. The 2D TVC makes the aircraft highly maneuverable, capable of near-zero airspeed at high angles of attack without stalling, and dynamic aerobatics at low speeds. The Su-30 MKI is powered by two AL-31FP afterburning turbofans. The TVC nozzles of the MKI are mounted 32 degrees outward to longitudinal engine axis and can be deflected a plus or minus 15 degrees in the vertical plane. This produces a corkscrew effect, greatly enhancing the turning capability of the aircraft. Examples of rockets and missiles which use thrust vectoring include both large systems such as the Space Shuttle Solid Rocket Booster, S-300P surface-to-air missile, UGM-27 Polaris nuclear ballistic missile and RT-23 ballistic missile and smaller battlefield weapons such as swingfire. The principles of air thrust vectoring have been recently adapted to military sea applications in the form of fast water jet steering that provides super agility. Examples are the fast patrol boat Vora MKIII, the Hammer-class missile boat and the U.S. Navy's littoral combat ships. A few computerized studies add thrust vectoring to extant passenger airliners, like the Boeing 727 and 747, to prevent catastrophic failures, while the experimental X-48C may be jet-steered in the future. List of vectored thrust aircraft. Thrust vectoring can convey two main benefits, VTOL/STOL, and higher maneuverability. Aircraft are usually optimized to maximally exploit one benefit, though will gain in the other. For VTOL ability: Bell Model 65, Bell X-14, Bell Boeing V-22 Osprey, Boeing X-32, Dornier Do-31, EWR VJ-101, Harrier Jump Jet, British Aerospace Harrier II, British Aerospace Sea Harrier, Hawker Siddeley Harrier, McDonnell Douglas Avenue 8B Harrier II. Hawker Siddeley Kestrel, Hawker Siddeley Pages 1127, Lockheed Martin F-35B Lightning II, VFW VAK-191B, Yakovlev Yak-38, Yakovlev Yak-141. For higher maneuverability, vectoring in 2 dimensions, McDonnell Douglas F-15 STOL MTD, Lockheed Martin F-22 Raptor, McDonnell Douglas 1036, Me-163B experimentally used a rocket steering paddle for the yaw axis, Sukhoi Su-30 MKI, vectoring in 3 dimensions, Sukhoi Su-35, Sukhoi Su-37, Sukhoi PAC-FA, Sukhoi HAL-FGFA, Microne MiG-35, McDonnell Douglas F-15 Active, General Dynamics F-16 Vista, Rockwell MBBX-31, McDonnell Douglas F-18 HARV, Mitsubishi ATDX, Other, 23 Class Airship, a series of British, World War I airships, Airship Industries Skyship 600 Modern Airship, Zeppelin NT Modern, Thruster Euro Vectoring Airship, see also. References. 8. Wilson, Eric A., An Introduction to Thrust-Vectored Aircraft Nozzles, ISBN 978-3-659-41265-3.